Is Erica Sturm, and I will be talking about machine learned spectra for the quantum impurity problem. I would like to thank my collaborators Matt Carbone from Columbia University, Dayu Liu from the Center for Functional Nanomaterials, Andreas Weichelbaum, and Robert Koenig, who are with me in the Condensed Matter Department, and we're all at Brookhaven National Lab. I would also like to thank the United States Department of Energy, Office of Science, for funding our work. We'll be discussing the single impurity Anderson model of a metal. Within this system, we have a conductor denoted here by the purple cross hatches, and here there are a sea of non-interacting fermions. These electrons do not see each other. However, embedded in this system, there is a single quantum impurity. This could be a single atom or it could be a quantum dot, and that is given here by the letter D. This exists at a chemical potential epsilon d below the Fermi energy here. At its lowest state, it's singly occupied with a single electron. However, if you want to doubly occupy it, you have to pay an energy cost of the Coulomb potential U, given here. Now, the lattice bath electrons do not talk to each other, but they do talk to the quantum dot here. And that interaction, that strength of connection, is controlled by a parameter known as the hybridization term, and that's gamma here in green. There are two conditions that we would like to study with this model, and those are the high and low Kondo temperature conditions. The higher one here is when the thermal energy dominates the interactions between that quantum dot and the surrounding lattice bath. Systems like this are treatable with perturbation theory and are generally well understood and well modeled. However, as the temperature drops, we access the low Kondo temperature condition, and here the thermal energy is no longer enough to allow electrons to come and go off the quantum dot and into or out of the lattice bath. These interactions are now controlled, instead of by the temperature, they are controlled by the coupling interaction J, which is defined as the hybridization term gamma divided by the Coulomb potential U. At this stage, electron movement becomes correlated, and perturbation theory will no longer work. These interactions are very important to us because they help explain things like magnetic phase changes and superconducting down at these lower temperatures. To investigate these systems is by way of the spectral function A omega. The spectral function describes the density of permitted quantum states as a function of the energy omega. So this isn't like an actual distribution of the states, it's just telling us what is permitted given the system parameters. This function is defined as the imaginary component of a single particle Green's function, given here in this equation. To generate one of these spectral functions, we utilize five physical input parameters: the Coulomb potential U, the hybridization constant gamma, the chemical potential epsilon d, the magnetic field strength B, and a thermal contribution T. Here we have a double peak structure that is symmetric with respect to omega equals 0, and that is because the chemical potential is equal to negative one half of the Coulomb potential. At the highest temperatures, we see the black curve, where there are just two peaks here. However, as the temperature begins to drop, we see the generation of this third central peak here. But notice these have all been normalized to 1, and so the fact that we're still at 0.18 says that while these are the permitted states, it's not very likely. Temperature drops even further, we access a new, that central peak becomes significantly stronger. This central peak is known as the Kondo peak. The other peaks are still present and they're still at the same heights that they were, but this Kondo peak is clearly the dominant permitted quantum state here. The Kondo temperature is always computed at T equals 0. Spectral functions that we can generate depending on whether or not a magnetic field is turned on, the relationships between the chemical potential, the Coulomb potential, and the hybridization term. So I've displayed several examples up here. These spectra can be generated by one of several different methods called quantum impurity solvers, and some of the more popular ones are the numerical renormalization group, quantum Monte Carlo, and exact diagonalization. These all have varying degrees of accuracy, however, they all come at a very high cost computationally. The goal here is that a machine learning approach could minimize this very expensive step by taking the same physical input parameters and generate the spectral function directly, or at least a good approximation to it. In this work, we generate the spectra with a numerical renormalization group, or the NRG, as described by Wilson. And we chose a feed-forward neural network due to the highly nonlinear relation between the input parameters and the output. Again, the input layer will have 5 physical features, and the output layer will be this spectral function, or an approximation to it. To generate our data, we use the QSpace tensor library developed by Andreas Weichelbaum at Brookhaven National Lab. We generated 1.45 million unique trials, and we classified them by condo temperature. We also utilized additional physical restrictions to target specific regions of our hyperspace for closer examination. The neural network was designed by Matt Carbone of Columbia University, and he used Keras with TensorFlow. And all of this was run on the free resources provided by the Google Co-Laboratory. Some of the technical details for our neural network include that we used the mean squared error loss function, the atom optimizer, and the rectified linear unit, or ReLU, for our interior activation functions. We also used mini-batching with 50 epochs, and depending on the region of hyperspace that we are targeting, this can take anywhere between 30 seconds and about 8 minutes to train our neural network. Results. On the left side of the screen, you can see the lower condo temperature regime, and on the right side condition, and on the right side, you can see the high condo temperature condition. Because these are two different regions of hyperspace, we trained on two totally different subsets for the training set and our relevant testing sets. These histograms are the errors for the associated testing set. The x-axis is a log scale, and the black lines are your deciles, the red line is your mean. And we can see in both scenarios the errors are tightly grouped, they are well distributed, kind of in a not quite bell curve. There is a little bit of skewing, but not too much. So we're actually very pleased with this. However, the goal was to generate spectra, not histograms. So here, let's look at a The top 10 graphs are of the low condo temperature condition, and the bottom 10 are the high condo temperature condition, where the black curve is the numerical renormalization group ground truth, and the red dashed lines are the neural network approximations. So you can see that in general, the neural network performs admirably. It is able to calculate where side features are, relative peak heights, peak widths. There are some rather significant errors in several of these graphs, but the punchline is that these are actually our 10 worst spectra for both the low and high condo temperature conditions. Remember, our testing sets were close to 20,000 trials each, and these are the absolute 10 worst of both of those 20,000 test trials. So to get a more accurate picture of what we can expect an average spectra. And here we can see that the peak heights are very well calculated, the widths are very accurate. We do have a couple of small little hiccups, but given that, for example here, the scale is so minimal that even these small errors look very large on this graph. So we're actually very excited by this because this is an enormous time saver for us, and it produces relatively accurate spectra. Final thoughts are that for a given region of the hyperspace, the neural network does an amazingly good job at making these approximations very quickly. The NRG trials take anywhere between 30 and 40 seconds to compute, whereas a trained neural network takes about a half second to make those predictions. So this represents an enormous speed up in time. Looking forward, short term, we would like one algorithm to predict all regions of the hyperspace, not just small subsets of it. To do this, we might need to parameterize or adjust the parameters or hyperparameters of the current neural network, or we may pursue reparameterizing the entire spectral function and utilize a different machine learning technique. Looking longer term, we might be interested in looking at more realistic systems with more than, say, one impurity, maybe there are multiple, or even have a non-constant hybridization term, again, that gamma. Instead of having a single gamma term, we might have a function for it, which is more realistic. We may also consider additional physical parameters. We are starting to think about transference learning with other quantum impurity solvers, and we are interested in pursuing potentially active learning, as opposed to this, which was a standard garden variety supervised learning approach. I would like to thank you for your attention and logging in to see my talk. I would be happy to answer any questions. Please contact me at the email that you see on the screen. Again, I would like to thank Brookhaven National Lab, Columbia University, and the United States Department of Energy Office of Science. And for additional work that my team is doing, check us out at CommScope. We are a team working on lots of cool stuff. Thank you for your attention and have a good day.